Okay, so let's get into it. We're going to do an explainer on how the internet sends information from one side of the world to the other in, the blink of an eye. It really does feel like magic, but underneath all that, it's actually one of the most elegant engineering blueprints ever created. I mean, think about it. We do this every single day without a second thought. You share a photo, you send an email, you stream a movie, but what is actually happening behind the screen when you hit send? How does that piece of data find its way from your device through this crazy maze of wires and signals all the way to the right destination? So, to break this all down, we're going to follow the journey of a single piece of data. Let's use this simple example. Sarah is sending a photo of her dog to her friend Max. We're going to track this photo from the exact moment Sarah hits send on her phone until it pops up looking perfect on Max's screen. Now, you might think this journey is just chaos, but it's not. It follows a very precise, internationally agreed upon blueprint that allows any two computers from any manufacturer anywhere on Earth to talk to each other. It's a system that's brilliantly built in layers. For any two devices to communicate, they need a shared set of rules. We call these protocols. And these protocols, well, they're basically the common language of the internet. They define everything, from how data should be formatted and addressed, to how to handle errors and make sure things actually get delivered. So here it is. This is the conceptual map for this entire process. It's called the OSI model. You can think of it as the perfect world blueprint for networking. What it does is it breaks this hugely complex task of sending data into 7 distinct manageable jobs, or layers. Each layer has one specific function, and here's the important part. It only has to talk to the layers directly above and below it. That modularity, that's the secret sauce. Okay, so while that 7-layer OSI model is our guide for understanding all the steps, the internet we actually use today runs on a more streamlined 4-layer model called TCP/IP. So why the difference? Well, TCP/IP was developed right alongside the early internet, which just made it simpler and more efficient in the real world. So we're going to use the OSI model to understand all the jobs, but you'll see how they map onto the real-world TCP/IP stack. Right, so before Sarah's photo can go anywhere, it has to be prepared for the journey. This process is called encapsulation. And honestly, the best way to think about it is like packing a letter for the post office. The data moves down this stack of layers, and at each step, a new wrapper with specific instructions gets added on top. The whole thing kicks off right at the top. The application layer is what Sarah's chat app is using. Then the presentation layer makes sure the photo is in a universal format. It handles stuff like compression and encryption. And right below that, the session layer acts like a coordinator, opening up a dedicated communication channel to Max's device. Next up, the data hits the transport layer, which basically acts like a shipping manager. See, a big photo file is way too large to send all at once, so this layer chops it into smaller, numbered chunks called segments. It also adds something called a port number, which is crucial for making sure the photo gets to the right application on Max's phone, his chat app, not his web browser, for example. And this is where a really interesting choice has to be made. The transport layer has to pick a protocol. For Sarah's photo, the app is going to use TCP. It's super reliable and make sure every single piece of that photo gets there. But for something like a video call or an online game, an app might use UDP instead, which prioritizes speed over the perfect delivery of every single packet. Let's keep moving down to the network layer. Here, each of those segments gets another wrapper, which turns it into what we call a packet. And this wrapper contains the most important address of all, the global destination, the IP address. You can think of this as the full mailing address on an envelope. It doesn't care how the letter gets there, it just specifies the final destination, guiding the packet all the way from Sarah's network to Max's. Okay, one final wrapper. The data link layer takes that packet and puts it inside something called a frame. Then it adds a totally different kind of address, the MAC address. This isn't the final destination, it's the unique hardware ID of the very next device on the journey. So if the IP address is the final destination city, the MAC address is like the street address of the next local post office it has to go to. So with all the addressing and packaging complete, the data has been fully encapsulated and is finally ready for its physical voyage. It's time to leave Sarah's device and enter the wild network. And this brings us to the very bottom layer, the physical layer. At this point, after all that prep, the fully prepared frames are converted into the most fundamental language of computers there is, binary code, just a simple stream of ones and zeros. And right here is where the digital becomes physical. Those ones and zeros are transmitted as electrical signals through an Ethernet cable, or as tiny pulses of light through a fiber optic cable, or as radio waves through the air for Wi-Fi. Sarah's photo is now officially on its way to Max. So what happens when those signals arrive at Max's phone? Well, the entire process just happens in reverse. It's a process called de-encapsulation. The data starts moving up the stack, and at each layer, the package is unwrapped and the instructions are read. So on Max's device, the data starts its journey back up the stack. First, the physical layer converts the incoming signals back into digital bits. The data link layer strips off its wrapper, checks for any errors. The network layer unwraps the packet and confirms, yep, this IP address is for me. Then the transport layer does its most important job. It waits for all those numbered TCP segments to arrive, puts them back in the correct order, and reassembles the complete photo file. Finally, the upper layers handle the session, decrypt the file, and deliver that perfect photo right to Max's chat app, ready to be viewed. And here's the part that's truly mind-boggling. This entire journey, from packaging to transport to unpacking, passing through all those layers on 2 different devices, happens in a literal fraction of a second. It's incredible. But this all raises a really important question, right? Why? Why use such a complicated, layered system just to send a photo? Why not just have one big program that does everything? Well, the answer to that reveals the true genius behind the internet's design. This layered approach is precisely what makes the internet so incredibly resilient, versatile, and, well, innovative. See, this modular design is everything. Because each layer has its own distinct job, you can innovate in one layer without breaking all the others. A new Wi-Fi technology at layer 1 doesn't require a whole new email protocol at layer 7. It makes troubleshooting so much easier, and it guarantees that any device from any company can seamlessly connect to the global network. So at the end of the day, it's not just a technical process. It's a shared global standard. It's a framework that has enabled decades of innovation and really underpins all of our modern digital communication. And that kind of leaves us with a final thought. This fundamental blueprint was designed when the internet was just in its infancy. So as we move into an age of quantum computing and the Internet of Things and connections that are woven into the very fabric of our world, what does the next blueprint for connection need to look like to last another 50 years?